Hello everyone. Today we are going to see a very practical demonstration of the real world application of linear regression to solve some problems. And the data set that we are using is a very famous Kaggle competition data set, which is the Boston housing prices prediction. So if you look at the data set, we have about 13 independent variables, and this is the definition of these variables. And based on these variables, we have to predict what would be the price of the houses. So if you can see, this MEDV is the median value of the owner occupied homes, which we need to predict based on the crime rate, the proportion of non-retail businesses. uh, RM would be the average number of rooms per dwelling, and you can definitely read more in the data set. So, without wasting any time, let us directly go how we are going to code this in the Kaggle platform. So, I'm just going to create a new notebook here. And let us start coding. So first and foremost, we need to import the libraries. The most important libraries would be NumPy as NP, import pandas as PD, import pborn as SNS, import matplotlib.pyplot as PLT. For linear regression, we're going to import stats models.api as SM, and I don't want warnings to be displayed, so I'm going to import warnings, and I'm going to filter the warnings. Warnings.filter warnings, and then ignore. So the first time when you run it with all these libraries, it is going to take a few seconds, uh, and that's fine. So after these libraries get installed, the most fundamental thing that we need to do is import the data set on which we need to analyze. There is some error. Let me see. So matplotlib dot, okay, the spelling is wrong, pyplot. It is pyplot SPLT. Okay, now it is running. So you can, the next thing we need to do is we need to add the data. So I'm going to click add data set, and I'm just going to type Boston data. Okay, so as you can see, there are so many people who have uploaded the data set, and I'm going to use any one of them. So I'm going to pick this Boston housing data set, and I'm going to click add. Okay, so I'm going to close this, and if I expand this, this is going to be the path of the data. So I'm going to copy this, and I'm going to read this file, pd.read underscore csv, and I'm going to see this data. So this is how the data set is looking, and I'm going to name this as data. So let us do some initial inspection of the data, where I'm going to write data.info. Okay, so there are about 506 observations, and we are lucky that we don't have any missing values or null values here. In a linear regression, we definitely want to see that there are not enough um, variations in the data in the sense that they are not outliers. So let me use a describe to check the outliers. Okay, so with this just one line of code, we get so many important metrics like what is the count of the observation, what is the mean value, standard deviation, minimum value, maximum value, different percentiles. So as you can see, uh, wherever there is a huge variation between the 75th percentile and the maximum value, it tells that there are a lot of outliers here, right? So for this, we have outliers. Similarly, for this variable, we have outliers. This also seems to be far off. For this, it's okay. But yes, you see, it is more than twice the 75th and the maximum. Okay, so definitely for some of the variables, there are outliers, and we would need to treat them because having outliers in the linear regression will not give the right coefficients, and our model will not be effective. So we would need to do some transformations with the data. Okay, so let us do some plotting to check some assumptions where we are able to see that okay, these variables, how are they related to our target variable? And the assumption is that there should be a linear relationship between these variables to the target variables. So let us do some pair plot to see. And this is data, and what is my x and what is my y. So y would definitely be my median value. And let me do one thing. Let me get the column names, data dot columns. Okay, so these are my columns, and I'm going to do a control C. So just to visually see and check if the variables have a linear relationship with the target variable, I've just done a pair plot here where my x variables are all the independent variables and y variable is the price of the housing. So if you just visually see, then let me zoom in. So for this, we can say that not very much a linear relationship here. Especially for this, we don't see any linear relationship. Maybe this one is a binary variable, so we are not going to have any relationship. But for this variable, for this RM, and I think RM is the number of rooms. As the number of rooms increases, the prices increases. So there is some linear relationship for this, but for age, for distance, um, okay, LStat was the ratio of the or the proportion of the population living in the lower status. So this is having some inverse relationship with the price. But overall, we don't see very much linear relationship for some of the variables. And this is a good thing to know and note as we will further proceed in our analysis, like which of the variables we need to drop and things like that. So this was a good visual analysis that we did. Second thing is we will remove the outliers because when we were looking at this, we definitely saw that there were some outliers. So the way to remove outliers can be multiple ways. We can just look at the box plots and try to remove the outlier values, or we can calculate what is the uh, outliers. So for example, as per the definition of outliers, it would be uh, uh, q1 minus 1.5 times of interquartile range. So there are some formulas as well, which we can apply to remove the outliers. So, but first, let us look at visually by using some box plots. Okay, so we can apply some box plots for these uh, these independent variables. But as you can see, if we apply using one by one, then it can become a very long exercise. So we can do some looping. Okay, and we can also do some subplots. Okay, so let us do some subplots. So the way we do subplots is we define a figure and we define the axis. We write plt subplots. Okay, and here we specify the number of columns we need and number of rows we need. Okay, and then we uh, the axis is for the number of columns and number of rows, and for the figure we just give the fig size. Okay, so definitely there will be a lot of subplots, so we would give a figure size of 20 to 10. So as you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so if we have 13 values to plot, so that's an odd number, right? So maybe we can do a 7 by 2 uh, thing, seven seven columns and 2 rows, so that will be like 14 plots, and the last plot will be vacant. Okay, so this we have um, made up the canvas of the plot. Then uh, we need to flatten the axis, because as you can see, this is a two-dimensional number of rows and number of columns. In order to iterate, we just need to have one dimensional. So for the axis, let us flatten the axis. Okay, and then we can use SNS library, and we can use a box plot. Okay, the data remains our data set, and in the axis we need to iterate with the axis. So let us loop now. For I dot call, in we use the enumerate function for our data columns. Okay, for each column we need to iterate, and what we're going to do is set axis with I, and we're going to set title as the column. So let us see. Okay, there is some error. We are doing the figure size. We are going to do flatten for I and call in enumerate. All right. There is some error. Okay, so this would be the right code for creating subplots. It is a bit confusing how to write or code for the subplots, but I just refined it to the correct format. So we first give the figure size, that what is the overall size of the plot that we want. using the plt.figure and fix size. And then we use the data dot columns, and we exclude the target variable, and we enumerate and try to extract the I and the column from this enumerate function, and then we use the subplots, uh, and then we add to the index 1 so that it can iterate, and uh, we use the box plot for each column. We are going to uh, plot, and then we can visually see uh, the the outliers for each variable. So now let us treat or remove some of the outliers, because outliers are not good for the analysis. So especially for this variable box plot for the number of rooms, right? We can remove some of the outliers here. We can also remove some of the outliers for zone. We can also remove some of the outliers for crime, and we can also do it for some LSTAT. So let us first write for what all we can remove. L LSTAT RM, mm, we can do it for ZN, and then we can do it for crime. And then we can visually see, right, that whether we need to exclude um, the top end outliers, or the lower end top layers. So accordingly we can remove them. Okay, so yep. So let us do for LSTAT first. So the formula is very simple here. We would do the we can take this variable, okay, and we can see the values, okay, but then we need to remove the top end, so we will take the quantile 75th 0.75, okay, or we is it the right spelling? Quantile. Okay, the spelling is wrong. Okay, so we get this quantile. Okay, so here is a quick formulas of how we can extract the outliers. So for example, if we want a higher quartile outlier, we have to find the 75th percentile, and we can add 1.5 times the interquartile range. So that is what I am doing it here. So I'm trying to find the Q3 or the 75th percentile, and then I'm going to add uh, so if you see in the definition, we are adding 1.5 times the interquartile range, 1.5 times the interquartile range, and interquartile range would be the 75th and the 25th percentile. So this 75 minus 25, right? So this is actually the higher end calculation, and anything above this 31 we are going to remove from the data set. So this would be the higher, or we can just use the higher higher outlier for L stat. Okay, so similarly I'm going to calculate the lower outlier and higher outlier for these four variables, and then we are going to remove them from the data set. So let me quickly calculate the outlier values for the four variables. So here we are. I have calculated the higher outlier range for all these variables and the lower outlier range of some of the variables. And this was only possible by visually looking at the variables and understanding that, okay, they are going to have outliers at the higher range or the lower range. So this really helps in calculating the outliers. So now after I've calculated the outlier values, I'm going to restrict the data by removing these outliers. Okay, so now let us remove the outlier values. So for that, I'm going to click at the data and we're going to do it one by one for each of these variables. So for example, for LSTAT, my data set is having these many values, but wherever the values are greater than the higher outlier range, I'm going to see that, okay, I'm going to create a boolean here, and then I'm going to filter my or subset my data like this. Okay, so this is the data set that I want in my machine learning. Okay, so similarly, I'm going to filter the data for the ZN. Okay, so for zone, these are my values. Okay, but okay, for zone, these are my values, and I'm going to have a higher outlier. So anything greater than this, okay, is something which I don't want, right? So I think here also I would need to do a less than, because I actually want in my data set anything which is less than. So this would be the right way to do it. So let me do it less than here and then subset the data. Okay. I think because I ran this with greater than, so let me do one thing. Let me run all and then we will proceed. Okay, so now we have the right data. Let me quickly see info now. Okay, so we initially started with some 500 observations, and now after removing some of the values, we have just 431 observations. That's fine. That's completely fine because we don't want outliers in the data. Okay, so let us remove the same for RM variable. Okay, so here we can do in one line that data RM. Okay, my values. Okay, one mistake I have done here is like for the higher outlier, it will be plus one. It will be plus one, plus one. Okay, for the lower outlier, it will be the 25th percentile minus 1.5, right? So because if we look at this, the lower is the Q1, that is the 25th percentile minus 1.5. So I have removed this here, and as you can see, now it is correct. I'll just rerun this code. Okay, and now when we click RM here, so now we want anything which is less than this. Okay, and here we can actually we can apply and here, right? and have two booleans at the same time. Anything which is greater than these ones. Okay, so now why is this not running? Okay, so I think it is not running because of the use of and. We can't use and, we have to use this operator. So now it is running. Okay, so now I want my data to be actually this. Okay, I'm going to save this. Okay, so similarly, I'm going to remove some of the outliers for crime. Okay, so now you can see that I have removed some of the outliers for this variable as well. And now when I look at the data info, we have about 355 observations. So as you can see, there's a 50% drop in data. Okay, not 50%. So from 506 to 355. So as you can see, there is so much transformations, and we need to clean the data before proceeding to the final machine learning model. So now we have checked the linearity assumption, whether the variables are linear or not. We have done the outlier detection, and let us see what are the variables which we can drop, because when we were looking at the pair plots, we definitely saw that some of the variables are not linear uh, in relationship to the target variable. So that is something we need to ensure, and the success of the linear model will only be decided based on the quality of the variables that we are having. So let us do a correlation plot. Okay, so I'm going to specify the figure size plt dot figure, that is the fixed size is equal to 10 comma 5. Okay, after specifying, we do a sns dot heat map data dot correlation. Okay, and I have to use the annotation as true. All right, so we can also apply formatting if mt is equal to zero point 0.1 format. Great. So this is the correlation matrix that we are seeing, and this will really help us in understanding which are the variables we need to drop, because definitely we have about 13 variables, and we don't want that many variables in our data. We only need to select the quality variables. So what we can see here is the lot of values, right? But we will only consider, we can take a threshold of 0.5, and anything above 0.5, we can include in our model, and rest we can exclude. Plus, if any two variables are showing a very high correlation, we can drop. So, for example, this RAD and crime, CRIM, they are showing a very high correlation. So, we can drop one of these variables. And really, it depends on which variable uh, we we think that based on intuition we can drop. Okay. So, for example, here, if you see this black, this is this, B is the percentage of black uh, people living in that area, and that is having a zero point 0.3 correlation with this. So we can drop this. Then we look at the Zen, this with uh, it's having a zero point 0.2 correlation. What else? DIS. is it's having 0.1. Okay, so any variable which is having zero point 0.1, zero point 0.2, zero point 0.3, we can remove them. So let me drop some of the columns. Data dot drop columns is equal to, we can give it a list. Okay, we don't want black, we don't want zn, and we don't want this. And then we'll give this, and then we can save this as a data frame. Okay, so now when we run this again, we see these correlations, right? There are some variables which are having still very low correlation, but let us not remove them, because some of them, such like taxes or the people teacher ratio, they seem to have uh, some effect, from an intuition perspective. So we will retain them as of now, and maybe later we can remove them. One of the things that you know we did not take into consideration is something related to the units. Okay, in linear regression we need to standardize some of the units, because age, for example, age and the price are in different units. So we can apply some standardization. And I think especially we can do some log transformations here. The log transformations which will actually help us in reading the coefficients in terms of percentage value. So what I see is the salary is in thousands of dollars. Okay, and tax is also in 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 dollar amounts. Okay, so we are going to do the log transformations for these two variables. So for example, data dot medv. Okay, let us transform this, is in a log format. So we will n numpy dot log, and wherever we do log transformations we need to add 1 here in this variable, just to nullify, because if any value is 0, then it will not give the correct result for log transformation. So we just added 1. So now this is the log transform values. So similarly we are going to do the log transformation for tax. Okay, and the reason we have done the log transformations is it will help us in reading the coefficients, and we will later see when we are interpreting the coefficients. Okay, so now our data is ready for our machine learning. So before we are going to do the splitting of train and test, we need to isolate the x and y variables, and the process is very similar to what we have demonstrated in our simple linear regression. We define x and we define y. Okay, so x would be my medv, and here data would be everything except the medv. So data dot, we can use data dot drop columns is equal to, okay, so if I look at x as this and y as this. Okay, so it is good that we convert them into array, because Okay, so now when we look as y, this is coming in arrays. Okay, I think when we are converting it into arrays, it is losing its column names. So let us keep in both of them in. Okay, let us keep them in the data frame format only, and we will see. So the second step is to add a constant. So when we look at x, okay, we need to add a constant here. So I'm using stats model sm dot add constant to x. Okay, so now you see there is a constant value of 1, and this is the price. So this would be my new x now. Okay, and then this is the y, and now it will become very easy. We will just use stats model ordinary least square, and what is my y variable and what is my x variable. I'm going to fit this, and I'm going to name this as model. Okay, and I'm going to do as model dot summary, just to see if things are working. Model dot summary. What is, okay, sorry, this is y. Okay, y is your median value and x is your, okay. Now let us do model summary now. Okay, great. Now we are getting an r square of 67, and then we are also looking at the p values. Okay, anything which is less than 0.05 is significant. Anything which is greater than 0.05 is not significant. Okay, so as you can see, age is not significant, not very much significant. And then these are the coefficients. So I think the model is running, and um, it is an acceptable 67% R square. But this is on the entire data set. And if you want to create a model, then we'll definitely have to do a train test split. So let us do a test split here. And the formula remains the same that we have used previously. X train, X test, Y train, Y test. And we use the train test split X. We specify X, Y, and then we do the random state is equal to maybe 100. Okay. And we give the test size is equal to 0.2. What is not running? Okay, we have not imported the library for train test split. So let me import here from sklearn dot model selection import train test split. Okay, so now if I run this, it should run. Okay, so we have now split the model, and we can apply the model. Okay, so for predicting, we will use the linear regression from the simple linear sklearn model. So from sklearn dot linear model import linear regression, linear regression. We create this class model from sklearn.linear model import linear regression, and in this model we will fit our x train and y train. Okay, so we are going to get this model, and based on this model we are going to predict. So model dot predict on x test, and this will be my y predicted. Okay, so let me see what is y predicted. Okay, but y test is this. Okay, this is my y test and this is my y predicted. So let us see what is the error between these two. Okay, we usually use the mean absolute error when we don't have any outliers, but in this data set there were some outliers. So let us do the mean squared error, and calculating the mean squared error is very simple. We will do sklearn dot metrics import mean squared error, and we will just write what is the mean squared error for the y test and the y predicted values. Okay, so this is the mean squared error, and I think this is 0.03, which is okay. It's not huge error. Okay, and but you have to note that these values are in the log format. Okay, we converted them into log transformations, but we can actually convert them into the normal numbers in which the initial units were. So let us also convert them, but first let us create a data frame, pd dot data frame. Okay, we're going to do a dictionary. So first we are going to see the y test values and then the y pred values. Okay, so let us do the y test values and y pred values, but let me rename the columns here. Like this is the y test, and same for here as well, that these are the actual values. Okay, actual. Okay, so these are my test values and these were my actual values. They're not very far from each other, as you can see. Let me name this as df, and now let me do the conversion np dot exp. This is how we convert back from log to the normal values. np dot df. So these are your actual values. Okay, so we have done the analysis in terms of uh, creating a model summary and reading the coefficients. And sometimes when we are doing an analysis, we need not always create a machine learning algorithm where we want to predict things. Most importantly, what we want to do is we want to read the coefficients. Okay, we want to read the coefficients and understand what are the drivers of the prices. So for example, how we read the coefficients here is very interesting. So first and foremost, because this is a multiple linear regression, we don't look at R square, we actually look at the adjusted R square. And the adjusted R square in this case is 0.66, which implies that 66% of the variation in prices is being explained by all these variables. Okay. And we have all these variables, but which of them are significant, right? And that is how we can see from the p-value. So anything which is greater than 0.05 is not significant. So for example, this variable index, this variable knox, this variable age, they are not significant. Remaining of them are significant. When they are significant, then the next question is how we are going to read this. Okay, so when we use the model, we have actually converted them in the log transformations. This uh, our the price variable is converted into log. So when we convert it into log, we read the coefficients as percentage change. So for example, if you look at uh, crime, okay, if the crime increases by 1 unit, the uh, the prices decrease by 3%. So because you can see these negative inverse relationship. As the crime increases, price decreases. This is a very simple interpretation just by looking at the negative sign. But then what percentage of the price decrease happens or price increase happens? Uh, we can read it like this. So if the crime increases by 1%, then the prices will decrease by 3.8 percentage. Okay, so that is how we read it. This variable is not important. This is the chas, and this is a binary, very important. So the uh, if the price increases, okay, if the or if there is a chassis river, the river is there, then the prices will increase by 12 percentage. So that is very significant. This one is not significant. Number of rooms is significant. So if the number of rooms increases by 1 unit, then the price increases by 7.9 percentage, almost 8 percentage increase in price. Okay, age is not significant. This is radius. I'm not sure what this is, what variable is this, but then if this increases by 1 unit, the price will increase by around 2 percentages. For and for tax also, this is important. If the tax will increase by one, the prices will decrease. So there's a negative relationship between prices and the taxes in those localities. People to teacher ratio, again, this is a negative relationship. And if the people teacher ratio increases by one, then the prices will decrease by around 3%. Okay. And then this variable LSTAT, this is also showing a negative relationship with the prices. And if this increases by one, then this is decreasing by 2%. One thing I missed here is we actually transformed the tags also in the log transformation. So if both of them are in the log transformations, then a 1 unit change in tags will actually reduce the prices by 0.23. It is not in 200, it is the prices will reduce by 0.23 because both of them are in the log transformations. So reading the coefficients to understand the drivers and the impact is very important. And this can be tricky sometimes. So make sure you read how to read the coefficients when we do the log transformations. So that would be very important. only one last thing that I would like to add here is adding the cross validation. So cross validation is important, uh, just to make sure that it is not an overfitting with what data that we have provided in terms of training and testing. So we can quickly do a cross validation here also, and then um try to take the mean score so that we see what is the error. Okay, so let us do the cross validation quickly, and for that we will use the sklearn library from sklearn dot model selection import cross val score, and here I'm going to use cross val score whatever model we have created, and the entire data set x and y. We'll do a 5-fold cross validation. Okay, so uh, this is the array of CV scores that we are getting. Okay, and what we're going to do is we are going to take the average of this. So let me name this as CV scores. Okay, and I'm going to take the mean of this, and the mean is 0.40. So this is wraps up your analysis, and I hope you found this useful. Thanks.